Topic 3D9, Trigonometric Identities. So when we talk about an identity, it's when an equation holds true for all values of the variable or variables. All right, for example, when we have x squared minus y squared, and we can factor that into x plus y times x minus y, that equation is always true for values of x and y. Therefore, it is an identity. Now there's a couple of identities that we're going to be using and practicing over the course of this lesson. The first one is our tangent identity. So tangent of theta equals sine of theta over cosine of theta. And if we kind of refer back to our original unit circle, and if we can remember that we can think about our opposite side from theta as representing our y, and our adjacent side from theta oftentimes representing our x. And because we know that in our unit circle our hypotenuse is 1, that the opposite side ends up representing our sine, and our adjacent x value represents our cosine, right? So in the same way, we can use what we know about tangent, right? So we already know tangent equals opposite over adjacent. And we know that our opposite side also represents our sine, and our adjacent side represents our cosine, right? Therefore, tangent of theta also equals sine over cosine. I use our unit circle just because our hypotenuse is 1. But regardless of if we're thinking about the unit circle or just any triangle in general that has the same hypotenuse, the hypotenuse value for sine and cosine ends up canceling out. So it doesn't matter whether we're talking about unit circle or any other kind of triangle. But the takeaway here is that we can replace tangent of theta into sine over cosine or vice versa. Our Pythagorean theorem identity similarly is derived from our unit circle and uses the Pythagorean theorem. So if we can imagine, we have our triangle like this. Our hypotenuse is 1, and then this side represents our sine because it is our y value, and then our x value is represented by cosine. And since we have a right triangle, we can kind of use that as sine squared plus cosine squared equals 1 squared, which we simplify to 1. So this helps us if we're trying to find either sine squared or cosine squared, or if we want to find one of those sine or cosine values, we can use our Pythagorean identity. Now, the last set of identities that we're going to talk about are our double angle identities. All right, so if we have some angle value, let's say this is 30 degrees, right? And we want to find sine or cosine of 60 degrees, double our original theta, then we can use a double angle identity. Now, since we just talked about the Pythagorean identity where we have cosine squared or sine squared, it becomes really, really, really important in using our identities that we're very clear if we're talking about a double identity like sine of 2 theta versus cosine squared of theta. All right, so squaring versus double our theta value, we have to be writing that very, very clearly. All right, our double angle identity for sine is just sine of 2 theta equals 2 sine theta cosine theta, where 2 sine and cosine are all just being multiplied. Cosine of 2 theta has 3 kind of identical derivations of our double angle identity. So you can use cosine squared theta minus sine theta, 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. And again, we can use any of those identities, and we can just think about what information is already provided to us and makes it easier to use one versus the other. Okay, so let's start off with let sine of x equal 2 over 3, where x is obtuse. All right, so there's a couple of things that's very important here. Number one, it tells us that x is obtuse, which means it is an angle measure between 90 and 180 degrees, putting us into our second quadrant. So if I'm going to draw kind of our triangle here, we're going to end up with something in our second quadrant, and we have some value of x, and it tells us our sine value. So sine is opposite over hypotenuse. So our opposite side is 2, and our hypotenuse side is 3. Okay, now this x value, I guess, is technically a little bit wrong. So let's actually get rid of that for a second. It's saying that this value here should be x. So let's just use theta here. And we can use theta to kind of think about that angle measure is going to be our reference angle, right? And if we wanted to, we could actually determine what our reference angle is by using our inverse sine, right? So if I did inverse sine of 2/3, I would get theta, which would equal approximately 41.8 degrees. Okay, just so we get an idea of what we're talking about, right? So then from 180, I can subtract 41.8 and end up with what is 138.2. Let me double check. 41.8, yeah, 138.2 degrees. So that's what our x value is, right? 138.2 degrees. And theta and x is actually not that important, right? None of our questions is asking what is x, what is theta. It's just, it gives us a frame of reference of what we're working with and looking at right now. Okay, so let's start with find cosine of x. So if we know that sine of x is 2 over 3, and we know that cosine is going to be adjacent over hypotenuse, there's essentially two ways to do it, right? And they kind of come from the same method. We can use the Pythagorean theorem, right? And then we can do 2 squared plus b squared equals 3 squared to get 4 plus b squared equals 9. Subtract 4 from both sides. B equals the square root of 5, right? So we know that this side will be the square root of 5. Cosine is going to be adjacent over hypotenuse, so then cosine of x will equal, we know that it has to be negative because we're in the second quadrant, negative root 5 over our hypotenuse 3. Or we could use our Pythagorean identity. So we can do cosine squared x plus sine squared x equals 1. So our cosine squared x is ultimately what we're going to try to look for, plus sine squared x. Well, we know that sine of x is 2/3, so we're going to take 2/3 and then square it, equals 1. Cosine squared x equals, cosine squared x plus 4 over 9 equals 1, and I'm going to subtract 4/9 from both sides. And we get 5 over 9, and then we take the square root of both sides. Cosine squared x equals the square root of 5 over 3, right? And now we just have to identify if we're talking about the positive or the negative. And here, again, we're in the second quadrant. our x value has to be negative. That's why this picture is so important. That's why reading this like obtuse part is so important. We have to be able to identify from this original picture that cosine has to be negative. Okay. So again, these are ending up giving us the same answer. So we can use either method, but our second method uses our Pythagorean identity. It just shows that our Pythagorean identity comes from, shockingly, the Pythagorean theorem. Okay, in order to find cosine of 2x, we can use any of our cosine 2x identities. Since we have sine and cosine of x, I've chosen to use our cosine squared theta minus sine squared theta identity, but you do not have to. Any of them will work. And I guess in a situation where maybe you're a little bit unsure if your cosine x is correct or not, it might make more sense to use this very last one, 1 minus 2 sine squared theta, since the sine squared value is given. Therefore, it has to be completely accurate. So cosine of 2x equals, now our cosine squared, so we're going to do negative square root of 5 over 3 quantity squared, minus our sine squared is going to be 2 over 3, and then that quantity gets squared. And now the negative square root of 5 quantity squared becomes 5 over 9, and then subtract 4 over 9. So cosine of 2x equals 1 over 9. But again, we have to think about if our original angle measurement is at 138.2, and then we're going to double that. Let's see where that puts us. 138.2 times 2 puts it at 276.4, right? So that gets us into the fourth quadrant, like this. And then if we have our cosine value, it's going to be adjacent over hypotenuse. You can tell that it's going to be a positive value. So here, we should have a positive 1/9. Okay? Go ahead and try student example number 1 on your own. Okay, teacher example number 2. Show that 1 minus cosine of 2 theta divided by 1 plus cosine of 2 theta equals tangent squared theta. Now I want to emphasize that problems that that look like this, that are asking you to prove that something is identical to something else, sometimes take some guess and check work. And sometimes you have to go down pathways that end up not being correct or getting you where you're trying to go. And that's okay. So sometimes these look messy. Sometimes you find ways that are a little bit more convoluted than like what the final answer will show. And again, that is okay. We're just trying to use the algebra that we're getting better and better at in order to determine what expressions are equivalent and how we can kind of simplify things and show that something is equal to something else, right? When I look at this, I can see that they have a cosine of 2 theta on my top and my bottom, right? And I just learned that there are multiple double angle identities for cosine. So I should start thinking, okay, are there any that have like sine and cosine since tangent is on my other side, right? If there's a way that I could get a sine in my numerator and a cosine in my denominator, maybe something will collapse into tangent. All right, so looking at that, that's kind of my original like initial first thought, right? But if it's not yours, guess and check, try other things out, see what happens as you play around, okay? My original idea here, I'm going to take this cosine of 2 theta and replace it with the double angle identity that uses sine. So I'm going to replace it with 1 minus, that part stays the same, I'm going to put it in parentheses, 1 minus 2 sine squared theta over, and then I'm going to replace the bottom double angle identity for cosine for the double angle identity that includes cosine. So it's going to be 1 plus 2 cosine squared theta minus 1. Okay, so both of those are our double angle identities. And all of that still is equal to tangent squared theta. Okay, since I have this negative here, I need to be able to distribute it. So I'm going to do 1 minus 1 plus 2 sine squared theta. And then in the denominator, I have a 1 and a negative 1. That's going to cancel out. So I'll have 2 cosine squared theta. And again, this equals tangent squared theta. And then again, I have this 1 minus 1 situation, which will cancel out. So I have 2 sine squared theta over 2 cosine squared theta, which equals tangent squared theta. And then I have a 2 that's dividing by 2. So now I just have sine squared theta over cosine squared theta, which equals tangent squared theta. And I know that's true because sine over cosine equals tangent. So I've just shown that tangent squared theta equals tangent squared theta. Problems like this, especially when it says like show that, ultimately does not need this as your final answer, right? Because it's telling you it will equal tangent squared theta. It's really looking for your process here. If your process is really messy, especially like on a test or somewhere else that's getting evaluated, it might be worth your time to rewrite it more cleanly so it's easier to follow, because it's a process that will be getting graded, not just like the end where you put tangent equals tangent. Okay, go ahead and try student example number 2 on your own.